The universe was dark for hundreds of millions of years. Then, a flicker, a single point of light tore through the endless void, and then another and another, until the cosmos itself caught fire. This was the beginning of the Cosmic Reionization Era, the universe's own turbulent teenage years. It is a chapter of cosmic history defined by chaos, transformation, and profound mystery. For over a decade, astronomers have been piecing together this story, yet for every answer, a dozen deeper questions emerge. By the end of this journey, you will understand the 25 greatest unsolved puzzles of this era, the very questions keeping scientists awake at night. What were the first sources of light, and could they have been something far stranger than stars? How did this explosive dawn shape the galaxies, including our own Milky Way that we see today? We are about to walk through the evidence, the theories, and the breathtaking frontiers of modern cosmology. What do you think it means to witness the universe waking up? Our first great mystery asks a fundamental question. What cosmic engine powered this transformation? What kind of celestial furnaces could produce enough raw, piercing light to strip electrons from atoms across the entire observable universe? The leading suspects are three, each more extreme than the last. The first and most elegant suspect is a generation of stars that no longer exist. Astronomers call them population 3 stars. These were the very first stars, born from pristine clouds of only hydrogen and helium, with no heavier elements to cool them down. This purity allowed them to grow monstrously large, perhaps hundreds of times the mass of our Sun. A star that massive lives fast and dies young, burning with a ferocious ultraviolet intensity that would make it a perfect reionization machine. But proving they were the primary culprits is difficult because these titans exploded long ago, leaving no direct trace for us to see. The second suspect is even more powerful and enigmatic. Quasars. These are the brilliant, violent cores of distant galaxies, where supermassive black holes feast on surrounding gas, blasting out torrents of energy that can outshine an entire galaxy. A single, bright quasar could reionize a vast bubble of space around it. The problem is timing. Were there enough of these monstrous black holes, grown to supermassive size so early in the universe, to do the job on a cosmic scale? Their formation itself is one of the great puzzles we will explore. Then there are the exotic possibilities, the wild cards that force us to question our most basic assumptions. Could the process have been fueled not by normal matter at all, but by the decay or annihilation of dark matter? It is a radical idea, suggesting that the invisible stuff that makes up most of the matter in the cosmos could have, in its own strange way, lit up the dawn. Each candidate leaves a different fingerprint on the pattern of reionization, a different signature in the faint light that has traveled for billions of years to reach us. So the hunt is not just for an answer, but for the right kind of evidence. Did the universe turn on its lights with the brilliant flash of the first stars, the focused beam of quasars, or a ghostly glow from the dark sector itself? The identity of the prime mover remains hidden, casting a long shadow over every other mystery of this era. But knowing what did it is only half the battle. The other half is figuring out when. The precise timeline of reionization is a detective story written in fading light, and the clues are frustratingly contradictory. When exactly did the cosmic light switch on, and how long did it take for the universe to become fully transparent? The answer is not just a date on a calendar. It is the key to understanding the growth of the very first structures in the cosmos. To solve this, astronomers turn to three powerful yet conflicting lines of evidence. The first comes from the oldest light we can see, the cosmic microwave background. This afterglow of the Big Bang carries a subtle imprint, a specific pattern of polarization caused by free electrons scattering light during reionization. This tells us the process was roughly halfway done when the universe was about 450 million years old. but it is a single, blurry snapshot of the entire event. For a more detailed movie, we look to the ghosts of ancient hydrogen. By studying the light from quasars more than 13 billion light-years away, astronomers see dark bands in their spectra called Gunn-Peterson troughs. These are the shadows of vast oceans of neutral hydrogen that existed before reionization was complete. The depth of these troughs suggests the universe was still murky with neutral gas when it was nearly a billion years old, hinting at a long, drawn-out process. Then there is the evidence from cosmic fireworks. The fleeting afterglows of gamma-ray bursts, even more distant than quasars, act as brilliant flashlights shining through the early cosmos. Their light also shows signs of being partially absorbed, but sometimes it tells a slightly different story, suggesting patches of the universe were clear earlier than the quasar data implies. So what is the truth? Did reionization start early and sputter along for hundreds of millions of years, or was it a rapid, dramatic firestorm? The data does not agree. A slow timeline means the first light sources were faint and scattered, struggling to carve out bubbles of ionized gas. A fast timeline points to an early population of incredibly powerful and efficient engines, like those monstrous first stars or plentiful quasars that flooded the cosmos with light in a relative blink. This is not just an academic debate. The speed of reionization dictates how quickly the first galaxies could form and evolve, shaping everything we see in the night sky today. It is the difference between a gentle dawn and a sudden, blinding sunrise, and we are still squinting at the evidence, trying to see which one truly happened. The timeline of reionization hinges entirely on the nature of the light sources, and this brings us to our third and perhaps most humbling cosmic mystery. What if the primary architects of this universal transformation were not the brilliant, rare monsters we have been searching for, but an immense, silent army of the small and the faint? For decades, astronomers have debated whether the countless faint, dwarf galaxies we see in the deepest images of the cosmos could have produced enough ultraviolet light to get the job done. These are not the majestic spirals we picture. They are tiny, chaotic smudges of light, each containing only a fraction of the stars in our Milky Way. The question is one of sheer numbers. Could there have been enough of these faint galaxies, each contributing a small trickle of ionizing photons, to collectively fill the cosmic bathtub? The answer lies in a deceptively simple curve that astronomers call the faint end slope of the galaxy luminosity function. In plain terms, this is just a cosmic census. It plots how many bright galaxies there are versus how many faint ones exist. If the slope is steep, it means the early universe was absolutely teeming with incredibly faint, tiny galaxies, far more than we can currently see. If the slope is shallow, then these faint galaxies were rare, and the heavy lifting must have been done by the brighter, rarer objects we have already considered. For years, our best telescopes could only see the tip of the iceberg, the relatively bright galaxies. We had to guess at the vast hidden population below. This meant our models of reionization were built on an assumption, a guess about an unseen multitude. Enter the James Webb Space Telescope. With its infrared eyes, Webb is not just looking farther back in time, it is looking deeper into the darkness. It is designed to see the faintest glimmers from the earliest epochs, to finally take that proper cosmic census. And what it is finding is already turning old ideas on their head. Webb is discovering galaxies that are both surprisingly bright and surprisingly numerous in the very early universe, galaxies that existing models said should not have had time to form. This suggests the population of light sources could be far richer and more complex than we ever imagined. It raises a thrilling possibility. Perhaps we have been missing not just a few faint galaxies, but an entire lost continent of them, a previously invisible realm of stellar nurseries whose combined output was the true driver of reionization. Or perhaps Webb is showing us that the first galaxies were simply more efficient at producing ionizing light than we thought. Either way, the story is being rewritten in real time. The faint end of the cosmic ledger is finally being filled in, and the balance of power for lighting up the universe is shifting before our eyes. Even if a galaxy produced a torrent of ionizing light, that light had to escape its own neighborhood to do its cosmic work. This is the heart of our fourth mystery, a critical bottleneck in the story of reionization called the escape fraction. In the simplest terms, it asks how many of those powerful photons actually made it out the front door. For every galaxy, this is a battle between creation and destruction. A galaxy might be a bustling factory of ultraviolet radiation, but it is also filled with thick clouds of gas and dust. These clouds are excellent at absorbing that very same radiation, turning the energy back into heat or scattering it into useless wavelengths long before it can reach the vast emptiness between galaxies. The escape fraction is just the percentage of ionizing photons that win this battle and stream out into intergalactic space. If the average escape fraction was very low, say only 5%, then the early universe would have needed a staggering, almost unimaginable number of galaxies to produce enough escaping light to complete reionization. If it was high, around 20 or 30%, the job could have been done by far fewer sources. But here is the problem: we cannot measure this number directly for the galaxies that mattered most, the ones during the reionization era itself. Their light is simply too faint and too redshifted for our current telescopes to pick apart in the necessary detail. Instead, we have to study nearby galaxies that we think might be similar, acting as cosmic analogs. What we find is a baffling inconsistency. Some galaxies, often smaller, more turbulent ones with powerful stellar winds blasting holes in their gas, appear to be quite leaky. They might let 10 or 20% of their ionizing radiation escape. Others, especially larger, more settled galaxies with calm, dense gas disks, seem to be almost completely sealed with escape fractions near zero. This variability is a nightmare for modelers trying to simulate the entire reionization process. Was the early universe dominated by leaky galaxies, making it easy for light to flood out? Or was it a mix where only a special subset of galaxies with just the right conditions became the effective beacons? The answer changes everything. It means that reionization might not have been a smooth, uniform process like a rising tide, but a patchy, stochastic one, driven by rare regions where galaxies were unusually efficient at venting their light into the void. This turns the cosmic landscape into a complex mosaic of bright bubbles and dark voids, a pattern dictated not just by where the galaxies were, but by what kind of galaxies they were on the inside. This patchy, inconsistent escape of light leads directly to one of the most profound shifts in our understanding of the era. Reionization was not a universal sunrise. It was a chaotic, fragmented dawn. Think of the early universe not as a dark room where someone slowly turns up a dimmer switch, but as a vast black canvas where someone is randomly striking matches. Each match is a galaxy or cluster of galaxies that has managed to leak its ionizing radiation. Around each successful source, a bubble of ionized hydrogen begins to form, expanding into the surrounding sea of neutral gas. For millions of years, the cosmos would have looked like a strange, cosmic Swiss cheese, with bright, transparent bubbles of ionized gas floating in a dark, opaque medium of neutral hydrogen. These bubbles grew, sometimes merging with neighboring bubbles when their edges touched, creating ever larger ionized regions. Eventually, after hundreds of millions of years, these bubbles overlapped completely, and the last isolated islands of neutral gas were finally evaporated away. The universe became transparent, but that journey from isolated bubbles to complete overlap is the key to everything. The pattern of those bubbles, their size, their distribution, is a frozen record of the first light sources themselves. A region dominated by a few monstrously bright quasars would have produced a few very large, quickly expanding bubbles. a region filled with a dense swarm of faint galaxies would have created a foam of many smaller bubbles that slowly grew and merged. By mapping this patchiness, we could literally read the blueprint of the early cosmos. So how do we see this pattern from 13 billion years away? Astronomers are waiting for a signal from the hydrogen itself. Neutral hydrogen emits a faint radio whisper at a very specific wavelength, 21 centimeters. During the reionization era, as bubbles of ionized gas grew, they would have carved holes in this pervasive 21-centimeter signal. By tuning our radio telescopes to the right frequencies, which correspond to different slices of time, we could, in theory, create a three-dimensional map of the era. We could watch the bubbles form, grow, and merge in a cosmic time-lapse. This is the grand promise of next-generation radio telescopes like the Square Kilometre Array. It would be the ultimate archaeological dig, revealing not just when reionization happened, but how it happened, street by street, bubble by bubble. It would show us the true architecture of the infant universe, a ghostly imprint of the first great battle between light and darkness. The hunt for those massive ionized bubbles leads us to a specific, terrifyingly powerful suspect: quasars. These are not just bright galaxies. A quasar is the core of a galaxy in its death throes, where a supermassive black hole, millions or even billions of times the mass of our Sun, is actively feeding. As matter spirals into the gravitational abyss, it heats up to unimaginable temperatures, blasting out a beacon of light so intense it can outshine every star in its host galaxy combined. A single quasar is a cosmic blowtorch, and its focused beam of ultraviolet and X-ray radiation is perfectly designed to strip electrons from hydrogen atoms. One powerful quasar could, in theory, ionize a bubble of space far larger and faster than any cluster of stars ever could. So the question becomes a matter of accounting. Were there enough of these cosmic monsters early enough to be the primary drivers of reionization? For years, astronomers scanned the deepest reaches of space, searching for the telltale pinpoint brilliance of high redshift quasars. Each discovery was a triumph, a glimpse of a black hole that had grown to gargantuan size when the universe was less than 1 billion years old, but a strange pattern emerged. The farther back they looked towards the very peak of reionization, the fewer quasars they found. These brilliant beacons, it seems, were astonishingly rare in the era that needed them most. This scarcity presents a fascinating paradox. If quasars were so rare, they could not have provided the bulk of the ionizing photons to light up the entire cosmos. Their overall contribution to the total energy budget of reionization might have been minor, perhaps only 10 or 20%, yet their individual impact would have been utterly dramatic. Imagine a vast, dark forest. Lighting it with 1 million candles would create a diffuse, even glow, but placing a single, brilliant searchlight in the center would create one overwhelmingly bright clearing with long, stark shadows at its edges. A lone quasar in the early universe would have done exactly that. It would have carved out one of the largest ionized bubbles imaginable, a colossal transparent region surrounded by a sharp, spherical boundary. Within that bubble, the conditions for galaxy formation would have been completely altered. The intense radiation would have sterilized the area, perhaps suppressing the birth of small, fragile galaxies, while its powerful jets could have triggered star formation in the dense gas at the bubble's edge. So while quasars may not have lit the whole party, they were likely the ones who blasted the music, creating the most extreme and influential environments in the young cosmos. Their rarity makes them not less important but more special. They were the chaotic architects, punching disproportionate holes in the darkness and sculpting the large-scale structure of the ionized universe in ways we are only beginning to understand. The paradox of quasars leads us back to a more primal, more universal suspect. Before galaxies had brilliant black hole hearts, before there were even galaxies at all, the cosmos was lit by a different kind of pioneer. These were the population 3 stars, the true firstborns of the universe. Their existence is theoretical, yet their legacy is written in the very atoms of our bodies. They were unlike anything that exists today, born from clouds of pure hydrogen and helium with no heavier elements to help them cool and fragment. They grew to staggering sizes. Imagine a single star, not 10, not 50, but 200 or 300 times the mass of our Sun. It would be a leviathan of nuclear fusion, a temporary, violent sun that burned at a temperature so ferocious its light was almost entirely in the hard, ionizing ultraviolet range. These stars did not live for billions of years. They lived for millions, a cosmic blink. Their entire life cycle was a race against gravity, and their deaths were as monumental as their births. A population 3 star faced 2 possible, equally catastrophic ends. If it was on the lower end of its impossible mass range, its core would eventually forge elements like carbon and oxygen, then iron. When fusion could no longer support its colossal weight, it would collapse and then explode in a supernova of such unimaginable power it would dwarf anything in the modern universe. This hypernova would blast the star's newly forged heavy elements out into the void. But if the star was truly a behemoth, perhaps above 260 solar masses, its fate was even more direct and terrifying. It would skip the supernova entirely. With no mechanism left to stop it, the entire star would collapse directly into a black hole. No explosion, no warning, just a silent, sudden descent into darkness. Both endings had universe-altering consequences. The supernova from these first stars were the universe's first alchemists. They polluted the pristine cosmic gas with the first traces of carbon, oxygen, silicon, and iron. Every element heavier than helium, the very stuff of planets and life, began with those cataclysmic explosions. This metallic pollution, as astronomers call it, changed everything. It allowed later clouds of gas to cool more efficiently and fragment into the smaller, longer-lived stars we see today. The direct collapse black holes, however, offer a solution to another profound puzzle. These stellar mass black holes, born from the very first stars, could have served as the perfect seeds for the supermassive black holes we find at the centers of galaxies. They would have had a head start of millions of years, sitting in the dense cores of early protogalaxies, greedily accreting gas and merging with one another. This could explain how quasars, requiring black holes of billions of solar masses, managed to exist when the universe was less than 1 billion years old. So we are left with a haunting thought. We will likely never directly see a population 3 star. Their era ended over 13 billion years ago, yet we see their ghostly fingerprints everywhere. In the faint chemical signatures of the oldest stars in our own galaxy, which contain traces of those first hypernova explosions, in the mysterious presence of supermassive black holes in the infant cosmos, and in the very atoms that make up our world. They were the universe's first great engines of change, whose brilliant lives and violent deaths set the stage for everything that followed. The violent deaths of those first stars did more than forge new elements. They seeded the cosmic landscape with a complex, wispy structure that would become the canvas for our next great mystery. To find it, astronomers don't look at galaxies or stars. They look at the empty spaces between them, using the most distant quasars as celestial flashlights. When the brilliant light from a quasar travels billions of light years to reach us, it passes through the vast, tenuous clouds of hydrogen that filament the universe. And on its journey, something remarkable happens. The light doesn't just pass through. It gets filtered, imprinted with the ghostly signature of every cloud it encounters. The result is a quasar spectrum, which should be a smooth rainbow of colors, transformed into a bizarre, comb-like pattern of dark spikes and troughs. This is the Lyman alpha forest. Each one of those hundreds, sometimes thousands, of dark absorption lines is a shadow. It is the fingerprint of a single cloud of neutral hydrogen, a whisper from a specific filament of the cosmic web at a specific moment in cosmic history. Think of it as the universe's most detailed fossil record, not of bones or shells, but of the diffuse gas that fills the voids. The properties of this forest changed dramatically during reionization. In the early, murky universe, the forest was dense and opaque, a thicket of dark lines because so much neutral hydrogen was present to absorb the quasar's light. As reionization progressed and those hydrogen atoms were stripped of their electrons, the forest began to thin. The darkest, broadest troughs, evidence of vast seas of neutral gas, slowly vanished, leaving behind the finer, more delicate lines we see from later, more transparent epochs. But this fossil record is incredibly difficult to read. The depth, width, and spacing of each line hold clues about the temperature, density, and motion of the gas cloud that created it. A thicker, smoother line might indicate a warmer, more turbulent cloud. A sharper, narrower line suggests a colder, calmer one. By studying the statistical properties of the entire forest, scientists can try to map the thermal history of the universe itself, tracing how the intergalactic medium was heated first by the first stars and then by the ongoing process of reionization. The challenge is that the signal is a chaotic overlay. The light has passed through clouds at all different distances, all moving at different speeds, all with different densities. Untangling this single, scrambled message into a coherent timeline is one of the most complex computational puzzles in modern astrophysics. It is like trying to reconstruct a symphony by listening to every single note played simultaneously. Yet within that cacophony lies the most detailed map we will ever have of the cosmic web in its infancy, a direct snapshot of the universe's skeleton as it was being assembled. That ghostly Lyman alpha forest holds a secret about the universe's temperature. Reionization was not a gentle process. Imagine those first ultraviolet photons as billions of tiny, energetic bullets. When they slammed into a neutral hydrogen atom, they did not just liberate the electron, they also gave it a tremendous kick, like a cue ball scattering the rack. This transferred energy heated the entire intergalactic gas, raising its temperature to a blistering 10,000 to 20,000 Kelvin. For context, the surface of our Sun is only about 5,800 Kelvin. So, in its youth, the thin soup between galaxies was actually hotter than the surface of a star. This aftermath, this cosmic fever, is a critical piece of the puzzle. We call it photoheating, and its precise evolution is a mystery with enormous consequences. The challenge is measuring it. We cannot stick a thermometer into a cloud of gas 13 billion light-years away. Instead, astronomers use the Lyman alpha forest as a cosmic thermometer. Remember, the width and shape of those absorption lines are sensitive to the temperature of the gas cloud that creates them. Warmer gas has atoms moving faster, which smears and broadens the absorption lines. Colder gas creates sharper, narrower lines. By analyzing the statistical properties of thousands of lines in a quasar spectrum, scientists can try to estimate the average temperature of the intergalactic medium at that specific slice of cosmic time. But the signal is incredibly subtle, buried in noise and complicated by other factors like the gas density and the expansion of the universe itself. Getting a clear temperature reading and, more importantly, tracking how it changed over hundreds of millions of years is like trying to chart the climate of ancient Earth using only a handful of blurry, overlapping tree rings. Yet, this thermal history is crucial because it dictated what happened next. This universal heating created a powerful form of feedback, a cosmic check and balance. Here is how it worked. After reionization, the intergalactic medium was hot and ionized. For a new, small galaxy to form, it needed to pull in this now hot gas and cool it down enough for it to condense into stars. But hot gas is puffy and energetic. It resists collapsing. Think of it like trying to inflate a balloon inside a hot oven. The heat fights against you. This photoheating feedback essentially raised the floor for galaxy formation. It became much harder for small clumps of matter, the kind that would have formed tiny dwarf galaxies, to gather enough cool gas to ignite new stars. The universe, in a sense, put a minimum size requirement on galaxy formation. Only the densest, most massive clouds of dark matter, those with a stronger gravitational pull, could overcome this hot intergalactic pressure and continue to grow. This process likely suppressed the formation of countless small, faint galaxies that would otherwise exist today. It sculpted the population of galaxies we see, favoring the growth of larger systems. So the mystery of the intergalactic temperature is not just about a number on a cosmic dial. It is about understanding a fundamental regulatory mechanism in the universe's growth. How hot did it get, and for how long did that heat persist? The answer determines how severely the formation of small galaxies was quenched, and therefore shapes the entire landscape of the cosmos we inherited. This universal heating may have solved one mystery while creating another that haunts our own galactic backyard. Look up at the Milky Way on a clear night. Our galaxy is not alone. It is surrounded by a swarm of smaller satellite galaxies, like moons orbiting a planet. But according to our most sophisticated supercomputer simulations of cosmic structure formation, there is a glaring problem. The simulations predict that the dark matter halo of a galaxy like ours should be teeming with hundreds, even thousands, of these small satellite galaxies. Yet we have only observed a few dozen. Where are all the rest? This is the famous missing satellite problem, and the fiery dawn of reionization may hold the grim answer. The smallest clumps of dark matter, those that would have become the tiniest dwarf galaxies, had a fatal weakness. Their gravitational pull was incredibly feeble. When the flood of ultraviolet radiation from reionization heated the intergalactic gas to those searing temperatures we just discussed, these puny halos faced an impossible task. They simply could not muster the gravitational muscle to pull that hot, puffy gas into their cores. Imagine a child trying to fill a balloon using only a weak, breathy whisper. The surrounding pressure is too great. For these potential galaxies, the gas remained forever out of reach, stranded in the hot intergalactic medium. Without cold gas to condense and form stars, these dark matter halos were stillborn. They exist, our simulations are sure of it, orbiting the Milky Way right now as vast, invisible shadows of pure dark matter. But they are utterly dark, devoid of the stars that would make them visible to our telescopes. Reionization, therefore, acted as a cosmic filter. It allowed only the halos above a certain critical mass with a strong enough gravitational grip to successfully capture gas and light up. This process likely suppressed the vast majority of what would have been a sprawling population of tiny, faint galaxies, so the satellites aren't missing. They are just hiding in plain sight, cloaked in permanent darkness, their potential for light snuffed out by the very event that illuminated the cosmos. This connection ties a modern observational puzzle directly to the ancient physics of the reionization era. It suggests that the fiery dawn did not just shape the distant universe, it carved the immediate neighborhood of our own galaxy, leaving behind a ghostly entourage of dark matter halos as silent monuments to its power. This cosmic filter of darkness and light leaves behind a ghostly whisper, a signal that could rewrite our entire understanding of the era. It is known as the 21-centimeter line, and its detection is one of the holy grails of modern cosmology. This is not a signal from stars or galaxies, but from the raw material of the universe itself. Neutral hydrogen, the most abundant element in the cosmos, has a tiny, intrinsic property. The single proton and single electron that make it up can exist in one of two very subtle energy states. When they flip from the slightly higher state to the lower one, they emit a photon with a wavelength of exactly 21 centimeters. It is an incredibly faint radio whisper, but because the early universe was filled with neutral hydrogen, this whisper was a universal chorus. As the universe expanded, that signal was stretched or redshifted to longer and longer wavelengths. By tuning our radio telescopes to different frequencies, we can effectively tune into different cosmic times. The dream is to create a three-dimensional movie of the universe's adolescence. We could watch the first stars ignite as subtle, localized dips in the signal. We could see the ionized bubbles around the first galaxies and quasars appear as growing holes of silence in the radio map. We could trace the exact progression of reionization from the first isolated bubbles to their final, complete overlap. This signal would be the ultimate direct probe, a live broadcast from the cosmic dawn. But listening for this whisper is perhaps the most difficult experiment in all of science. The first challenge is sheer weakness. The signal is billions of times fainter than the cacophony of radio noise from our own galaxy and from human civilization. It is like trying to hear a single snowflake land in the middle of a rock concert. To overcome this, astronomers build their telescopes in the most remote radio-quiet zones on Earth, like the deserts of South Africa or the outback of Western Australia. They use enormous arrays of simple dipole antennas, like the Hydrogen Epoch of Reionization Array, or HERA, which looks like a sprawling field of metal spiderwebs. These arrays don't make pretty pictures, they collect petabytes of raw data to statistically hunt for the signal's subtle imprint. The second challenge is calibration. The interference from our own atmosphere and the ionosphere is a massive, shifting curtain of noise. Even the radio glow from our galaxy's synchrotron radiation is a foreground signal 1,000,000 times brighter than the target. Separating the faint cosmic whisper from this overwhelming terrestrial and galactic static is a computational nightmare. It requires building exquisite models of every known source of interference and subtracting them with near-perfect precision. A tiny error could either erase the real signal or create a false one. So what happens if, after all this, we finally hear it? A clear detection of the 21-centimeter signal would be a revolution. It would give us our first true map of the early cosmic web, confirming or refuting every model we have about the timing, the patchiness, and the sources of reionization. It could reveal the properties of the very first stars before they ever formed galaxies. And if we do not detect it where our theories predict, that could be even more profound. A non-detection might mean our understanding of the early gas conditions is fundamentally wrong, or it could point to exotic new physics, perhaps an unexpected interaction between dark matter and hydrogen that cooled the gas more than we thought. The great radio silence itself would then become the signal, a message that the universe's first chapters are stranger than we ever dared to imagine. Ultraviolet light was the star of the show, but it did not work alone. Lurking in the wings were other, even more energetic forms of radiation that could have shaped the drama in profound ways. This brings us to the role of cosmic rays and X-rays. While ultraviolet photons have just enough energy to strip an electron from a hydrogen atom, X-rays pack a far more powerful punch. They are born in the most violent environments imaginable, the searing aftermath of a supernova, the frenzied jets of a microquasar, or the intense heat of gas spiraling into a black hole in a binary star system. Their unique power lies in their ability to penetrate. A cloud of neutral hydrogen that would completely block ultraviolet light is often transparent to an X-ray photon. This means X-rays could travel vast distances through the murky, pre-reionized universe, reaching deep into regions that ultraviolet light from the first stars could not yet touch. When one of these high-energy photons finally did collide with an atom, it did not just liberate a single electron. It acted like a cannonball, blasting the electron free with so much leftover energy that the electron itself became a weapon, zipping through the gas and ionizing many more atoms in a cascade of collisions. This process, called secondary ionization, could have been a crucial multiplier effect, but the influence of X-rays may have been even more subtle and preparatory. By flooding the cosmos with this penetrating radiation long before the main ultraviolet onslaught, they could have performed a cosmic preheating, Imagine trying to melt a block of ice with a blowtorch. If you first warm the entire block gently with a hairdryer, the final melting happens much faster and more evenly. X-rays could have acted as that universal hairdryer, gently warming the vast reservoirs of neutral hydrogen, making the gas slightly more energetic and less tightly bound. This would have made the subsequent job of the ultraviolet photons far easier, allowing the ionizing fronts from the first galaxies to propagate faster and carve out larger bubbles. So were X-rays and cosmic rays just minor supporting actors, or were they the indispensable stagehands that set the scene for the main performance? The answer depends on how abundant these high-energy sources were in the very early universe. If the first stars died in frequent, clustered supernova, or if early black hole binaries were common, their diffuse X-ray glow could have been a pervasive and transformative background hum. This would paint a picture of reionization as a two-act play, a long, slow preheating by X-rays, followed by a rapid, decisive ionization by ultraviolet light. If these sources were rare, then their role was more localized, perhaps only important near the sites of extreme violence. Unraveling this mystery requires looking for the fossilized thermal imprint of this preheating in the ancient intergalactic gas, a faint signal that next-generation observatories are now hunting for. It reminds us that the dawn of light was not a monologue but a complex chorus where even the deepest, most penetrating voices played a part in shaping the cosmic landscape. The universe's first chemistry set was not a gentle experiment. It was a series of colossal, catastrophic explosions. For hundreds of millions of years, the cosmos was a pure, simple place, composed only of hydrogen, helium, and a trace of lithium. Every atom of oxygen you breathe, every speck of carbon in your body, every particle of iron in your blood did not exist. Then, the first generation of massive stars reached the ends of their brief, furious lives. Their cores became furnaces where nuclear fusion forged new, heavier elements. And when these titans died in hypernova, they did not fade quietly. They detonated, scattering their freshly minted atomic ash across thousands of light years. This was the universe's first act of pollution, and it changed everything. We call this process chemical enrichment, and its pace during the reionization era is a profound mystery. How quickly did the cosmos go from pristine to peppered with these heavy elements, which astronomers poetically call metals? The answer is written in the oldest stars we can find. Some ancient, surviving stars in the halo of our Milky Way have incredibly low metal content, just 1/10,000th of the Sun's abundance. They are living fossils, formed from gas that was only lightly seasoned by the very first supernova. Their existence tells us that the initial enrichment was incredibly patchy. Vast regions of space might have remained chemically pristine for a long time, while bubbles around the first star clusters became rich in metals almost immediately. This uneven spread meant that the second generation of stars could have wildly different properties depending on where they were born, some from pure gas and some from already polluted material, leading to a chaotic diversity in the early stellar population. But those supernovae did more than just spray atoms. In their violent ejecta, as expanding gas cooled, something miraculous happened. Atoms like carbon, silicon, and iron began to stick together in tiny clusters, forming solid particles smaller than a wavelength of light. This was the birth of the first cosmic dust. Think of it as soot from the universe's first great fires. This dust adds a fascinating and complicating twist to the story of reionization. Remember the critical problem of the escape fraction. How many ionizing photons get out of a galaxy? Dust is a master of absorption. Those same hard ultraviolet photons that can strip electrons from hydrogen are also perfectly tuned to be absorbed by tiny dust grains, which then re-radiate the energy as harmless, lower-energy infrared light. So, if a young galaxy contained even a small amount of this early dust, it could have acted like a cosmic sponge, soaking up the very photons needed to ionize the universe and trapping them inside. This creates a counterintuitive feedback loop. The first stars produce metals and dust. That dust then hinders the escape of ionizing light from later stars, potentially slowing down the reionization process. But if reionization slows, more stars have time to form and produce even more dust, making the problem worse. Did early galaxies quickly become so dusty that they choked on their own light, or was dust so rare that it was a minor concern? We simply do not know. The James Webb Space Telescope offers a clue as it peers at galaxies from this era. It is incredibly sensitive to infrared light, the very signature of dust-warmed radiation. If Webb sees galaxies that are bright in infrared but faint in ultraviolet, it would be strong evidence that dust was already playing a major role, cloaking the young stellar populations and locking their ionizing power within. This turns the build-up of metals and dust from a side effect into a central character. It was not just the outcome of the first stars, but an active participant that could have governed the speed and efficiency of the cosmic dawn itself, a shadowy regulator born from the ashes of the very engines it sought to control. Dust and metals were not the only legacy of those first stellar explosions. They also left behind the deepest gravitational scars in the universe. The brilliant quasars we detect from the reionization era are powered by supermassive black holes, some containing over 1 billion times the mass of our Sun. Their existence so early in cosmic history presents a monumental timing problem. How do you build a gravitational monster of that scale in less than 1 billion years? It is like finding a fully grown sequoia tree in a garden that was only just planted. This is not just a curiosity, it is a fundamental crisis for our models of cosmic growth. A black hole cannot simply eat its way to that mass from nothing. It needs a starting point, a seed, and then it needs to feed at a breakneck pace for its entire existence. So what were those seeds, and how did they find such an extravagant banquet so quickly? One leading theory points back to the death of the first stars. The most massive population, 3 stars, those that collapsed directly into black holes without a supernova, could have left behind seeds of perhaps 100 solar masses. That is a great head start, but the math is still punishing. To reach 1 billion solar masses, that seed would have to accrete gas at the maximum theoretical rate, called the Eddington limit, for its entire life, never pausing, never starving. It is a precarious and unlikely scenario, like demanding an infant never stop eating from the moment it is born. This difficulty has led scientists to consider a more dramatic birth. Perhaps the seeds were never stellar at all. In the dense, chaotic cores of the very first protogalaxies, enormous clouds of pure hydrogen gas might have collapsed under their own weight so violently that they skipped the star formation stage entirely. With no heavy elements to cool the gas and allow it to fragment, the entire cloud, weighing tens of thousands of solar masses, could have plunged directly into a single, massive black hole. This process, known as direct collapse, creates a ready-made superseed, a behemoth from day one that would have a much easier path to becoming a supermassive object. But it requires very specific, pristine conditions, a gas cloud that remains untouched by the metal pollution from earlier stars, and bathed in a strong background of ultraviolet light to prevent it from cooling and forming normal stars first. These conditions might have been rare, but in the early universe, perhaps they were just rare enough to create the monsters we see. There are even more exotic possibilities. Could these black holes be primordial, formed not from collapsing stars or gas, but from ultra-dense fluctuations in the fabric of space-time in the first fraction of a second after the Big Bang? If so, they would have been present from the very beginning, sleeping giants that simply awoke and began to feed when the first gas clouds fell into them. Each of these origin stories leaves a different mark on the reionization process itself. A universe where black holes grow from direct collapse seeds would see powerful quasars igniting earlier and more efficiently, blasting out focused bubbles of ionized gas. A universe reliant on slower growth from stellar seeds might have a more delayed and patchy quasar contribution. The growth of these black holes is not a separate story. It is the dark, driving engine of the era. Their ferocious feeding produced the ultraviolet and X-ray radiation that heated and ionized their surroundings. Their powerful jets could have stirred the cosmic pot, triggering or suppressing star formation in their host galaxies. They were not just passengers in the reionization era, they were some of its most influential architects. Solving the mystery of their impossible birth is therefore key to understanding the entire character of the cosmic dawn. We are left wondering if the brightest beacons in the early universe were born from the silent collapse of dark, pristine clouds, or if they grew from the ashes of the very first brilliant stars. That dark legacy of suppression casts a long shadow, directly sculpting the types of galaxies that could survive and thrive. This is the profound impact of reionization on galaxy formation itself. The universe's great ultraviolet background did not just illuminate the cosmos, it established a set of cosmic rules. It created a minimum mass requirement for a galaxy to even exist. To understand why, picture a small, fragile cloud of dark matter, a halo just beginning to pull in the surrounding gas. Before reionization, that gas was cold and neutral, easy to condense. But after the flood of ultraviolet radiation, that same gas was now hot and ionized. Hot gas is energetic, it has pressure, it resists being squeezed into a small space. For a tiny halo with weak gravity, this was an insurmountable barrier. It was like trying to fill a child's inflatable pool using a fire hose. The pressure of the incoming water would just blow the pool apart. The hot gas simply could not cool down and collapse into the halo's core. Star formation was strangled before it could even begin. These small potential galaxies were permanently quenched, left as dark matter ghosts. But for a larger, more massive dark matter halo, the story was different. Its gravitational pull was a mighty fist, strong enough to overcome the pressure of the hot gas and drag it inwards. Once inside the deep gravitational well of a large halo, the dense gas could finally cool, often through collisions that radiated energy away, condensing into the first stellar nurseries. This critical divide, this minimum mass, became a fundamental filter for the universe. It meant the smallest, faintest galaxies we might expect from pure dark matter simulations simply never got a chance to shine. The cosmic dawn didn't just light up the universe, it pruned its family tree. It ensured that the dominant population of galaxies would be above a certain size, directly influencing the demographics of galaxies we see in our local universe today. This suppression effect also helps explain the large-scale architecture of the cosmos, the cosmic web. The regions that were reionized earliest became hostile environments for small galaxy formation, while the slower, darker patches might have sheltered a last generation of tiny galaxies. So the pattern of galaxies we see is not just a map of where matter collapsed, but a fossil record of where and when the ultraviolet firestorm passed through, a permanent scar on the distribution of light in the universe. The universe's grand filter left behind a haunting question about its final act. Did the cosmic dawn end with a decisive, brilliant flash, or did it simply fade into the light of day? We call this the conclusion of reionization, but pinning down its final moments is a challenge in cosmic archaeology. Officially, the era is thought to have wrapped up when the universe was roughly 1 billion years old, a point marked by a redshift of about 6. The evidence from distant quasars suggests that by this time, the vast, opaque seas of neutral hydrogen were mostly gone. The light from these brilliant beacons could travel almost unimpeded, indicating a cosmos that had become largely transparent. But largely transparent is not the same as perfectly clear. Think of a foggy morning. The official sunrise might burn off the thick blanket of fog, but wisps and tendrils can linger in the valleys and shadows long after the sky is officially blue. The same might be true for the young universe. the last pockets of neutral hydrogen would have been the most stubborn, isolated in the hardest-to-reach places. They might have been tucked away in the densest cores of diffuse cosmic filaments, the sprawling highways of the cosmic web where gas was too thick and self-shielding for ultraviolet radiation to penetrate fully. Or they could have survived within the hearts of the smallest, darkest dwarf galaxies, those that just barely managed to form a few stars but whose own feeble radiation couldn't ionize their own dense gas, and which were too isolated for external light to reach. These would have been cosmic holdouts, tiny islands of primordial fog in an otherwise clear sky. The question is whether these holdouts were swiftly evaporated by a final, concerted push of ionizing radiation, or whether they lingered for hundreds of millions of years more as the universe's production of new ionizing photons began to slow. This is the difference between a clean cut and a long fizzle. A clean, sharp end suggests the ionizing sources were still going strong, efficiently hunting down and eliminating the last remnants. A fizzle implies that the photon budget was running low. Perhaps the most massive, efficient stars had died off, and the remaining galaxies were less prolific producers of the hard ultraviolet light needed for the final push. Some tantalizing clues point to a drawn-out finale. Observations of galaxies from just after the supposed end of reionization show signs that their light is still being slightly absorbed by small amounts of neutral gas. It is a faint signal, like seeing a distant street lamp through the last remnants of a mist. This hints that the process might not have had a single, universal off switch. Instead, reionization could have ended at different times in different places, with the last neutral atoms finally being stripped away in a slow, uneven whimper rather than a synchronized bang. The fate of these final atoms is more than a technical detail. If neutral hydrogen persisted in the cosmic filaments, it could have provided a lingering source of cold fuel for later generations of galaxies, subtly influencing their growth. It means the boundary between the era of first light and the universe that followed might be beautifully, frustratingly fuzzy, a gradual transition where the last echoes of the cosmic dawn took an extraordinarily long time to finally fade into silence. The lingering fog of the final neutral atoms presents a cosmic paradox. How can we measure something so diffuse and ancient across the entire sky? The answer is written in the oldest picture we have of the universe, but you have to know how to look at it. The cosmic microwave background is more than a baby picture of the cosmos. It is a detailed fingerprint, and within its subtle patterns of polarization lies a direct echo of the reionization era itself. To understand this, think of the CMB light as a gentle sea of waves. Originally, these waves vibrated in all directions equally, but about 400,000 years after the Big Bang, when the universe cooled enough for atoms to form, something critical happened. For the last time, those CMB photons scattered off free electrons. This final scattering event imprinted a specific pattern of polarization on the light, like combing the waves to align in a particular direction. This is what we call the primary CMB polarization. Fast forward hundreds of millions of years to the reionization era. The universe is once again flooded with free electrons, this time created by the first stars and galaxies stripping hydrogen atoms apart. As the ancient CMB photons from the Big Bang journey through this new electron soup, a small fraction of them, about 1 in 3,000, scatter one more time. This late-time interaction does not create the primary pattern. Instead, it overlays a new, fainter signal on top of it, specifically at the largest angular scales on the sky. Astronomers call this the reionization bump. It is a subtle, broad hum in the polarization data that tells a powerful story. The strength of this bump is directly proportional to the total number of free electrons the CMB photons encountered during reionization. In essence, it gives us an all-sky average, a single, integrated number that tells us how much ionizing activity happened over the entire course of the era. It is like measuring the total amount of dye released into an ocean over time by looking at the final, uniform tint of the water. This measurement is incredibly powerful because it comes from a completely independent source than quasars or galaxies. It does not tell us about patchiness or timing in detail, but it provides a critical anchor point, a global check on the total energy budget of reionization. To decode this faint whisper, scientists separate the polarization signal into two distinct types, named E modes and B modes. E mode patterns look like radial or concentric patterns, like the petals of a flower or contours on a map. They are created by ordinary density fluctuations, including that final scattering from reionization. B mode patterns have a curling, swirling character, like the pattern of water going down a drain. Primordial B modes would be a smoking gun for gravitational waves from the Big Bang's inflationary epoch, a monumental discovery in its own right. The challenge is that the reionization signal is buried within the much brighter primary E modes and is also contaminated by B modes created later by gravitational lensing, where the CMB light is bent by the mass of all the cosmic structure in its path. Isolating the reionization bump requires exquisite sensitivity and precision. This is the driving goal of next-generation observatories like the Simons Observatory and the future CMB Stage 4 project. These are not single telescopes, but vast arrays of ultra-sensitive detectors placed in the high, dry deserts of Chile and the South Pole, where the atmosphere is transparent to microwave light. They are designed to map the CMB's temperature and polarization with a fidelity we have never before achieved. By measuring the precise shape and amplitude of the reionization bump in the E-mode data, they will pin down the total optical depth caused by those reionization era electrons. This one number will tightly constrain the entire history of the era. Did reionization happen early and fast, producing a lot of free electrons quickly? Or was it a long, drawn-out affair with a lower overall electron count? The polarization of the ancient afterglow holds the answer, a faint but universal record of the universe's second great encounter with light. That faint echo in the cosmic microwave background gives us a crucial number, but it also sets up a demanding cosmic ledger. We must now ask the ultimate accounting question of the reionization era. Did the universe have enough money in the bank in the form of ionizing photons to pay for its own transformation? This is the Lyman continuum photon budget, and balancing these books has become one of the most pressing crises in modern cosmology. Lyman continuum photons are simply the specific, high-energy ultraviolet photons capable of prying an electron from a hydrogen atom. They are the currency of reionization. To complete the process, you need a staggering number of them. For every single hydrogen atom in the intergalactic medium, you need at least one of these photons to ionize it. But the universe is not perfectly efficient. Many photons are wasted, absorbed by dust or by hydrogen atoms inside their own galaxies before they can even escape. Others are lost simply because an already ionized atom cannot be ionized again. So, in reality, you need many more photons than there are atoms, perhaps 10 or 20 times as many, just to be sure the job gets done. The crisis emerges when we try to do the math with the galaxies we can actually see. Astronomers take deep-field images from telescopes like Hubble and now Webb, count all the galaxies from the reionization era they can detect, and estimate how many Lyman continuum photons each one should be producing based on its size and star formation rate. Then they apply a reasonable guess for the escape fraction, the percentage of those photons that actually leak out into intergalactic space. When they add it all up, the numbers often come up short. The observed galaxies, even with optimistic assumptions, sometimes seem to produce only half or two-thirds of the photons needed to reionize the universe within the timeline suggested by other data. It is as if we have found the bank statements showing a massive withdrawal, but when we count the cash in all the known accounts, there is not enough money to explain it. This is the photon budget shortfall. It forces astronomers to confront several uncomfortable possibilities. Perhaps our estimates for the escape fraction are far too low, and early galaxies were incredibly leaky, venting 40 or 50% of their ionizing radiation. Or perhaps we are still missing a vast population of galaxies too faint for even the James Webb Space Telescope to see easily. A hidden legion of tiny stellar factories whose combined output fills the gap. There is a more exotic third option. Maybe we have the galaxies right, but we are wrong about how the photons were used. Could the process have been more efficient than we think? If the ionized bubbles around galaxies overlapped in a very specific, non-wasteful way, or if the intergalactic gas was preheated and easier to ionize, then perhaps fewer photons were needed overall. Each solution points to a radically different early universe. A high escape fraction means early galaxies were fundamentally different from their modern counterparts, perhaps more turbulent and porous, with stellar winds blasting clear pathways for light. A missing population of ultra-faint galaxies suggests the cosmic dawn was lit by a dim, ubiquitous glow from countless specks of light, rather than a few brilliant beacons. This accounting crisis is not just a technical dispute. It strikes at the heart of our understanding of the first billion years. It tells us that our census of the early cosmos is still incomplete, that the story we are piecing together from shimmering points of light in deep field images is missing entire chapters. The balance sheet of the cosmic dawn remains unbalanced, and until we find those missing photons, we cannot truly say we understand how the lights came on. The shape of the cosmic dawn holds secrets about its creators. We have spoken of bubbles, but that word is almost too simple. In reality, the topology, the three-dimensional geometry of the ionized regions, was a complex and evolving sculpture carved by light into the dark hydrogen sea. Were these regions perfect spheres, like soap bubbles blown from a single, brilliant source? Or were they strange, elongated filaments tracing the underlying skeleton of the cosmic web itself? The answer is a direct fingerprint of the light sources that made them. Imagine a single, powerful quasar, a cosmic lighthouse. Its radiation blasts out in all directions with ferocious intensity, overwhelming the surrounding gas equally. It would carve out a roughly spherical ionized bubble, expanding outward in a wave. The boundary of this bubble would be sharp, a clear wall separating the brilliant interior from the opaque exterior. Now picture a dense cluster of early galaxies, not one brilliant beacon but a swarm of fireflies. Each galaxy creates its own small ionized region. As these regions grow, they do not expand into a uniform void. They expand along the paths of least resistance, following the dense filaments of gas that already connect them in the cosmic web. When these individual bubbles finally touch and merge, they do not create a perfect sphere. They create an irregular, interconnected foam, a labyrinth of ionized tunnels tracing the web's filaments, with remaining pockets of neutral hydrogen trapped in the emptier voids. This distinction is crucial. A universe where reionization was driven by rare, brilliant quasars would have a topology of isolated, large spheres. A universe lit by countless faint galaxies would show a topology of complex, webbed filaments. The geometry tells the story. This is why the promise of 21-centimeter tomography is so revolutionary. It would not just show us where the bubbles were. It would show us their precise shapes in 3 dimensions, a full architectural blueprint of the young cosmos. By analyzing the connectedness of the ionized regions, scientists could perform a cosmic autopsy. They could measure the characteristic size of the bubbles at different times. Were they large and isolated early on, pointing to powerful individual engines? Or were they small and numerous, quickly linking into a complex network, indicating a dense population of smaller sources? The topology would even reveal how the sources were clustered. Did the first luminous objects huddle together in dense knots, creating huge, merged ionized regions early in certain areas? or were they scattered evenly, leading to a more uniform progression? This structural evidence would be the most powerful tool we have to finally settle the debate between galaxy-dominated and quasar-dominated reionization. It moves us from counting photons to reading the map they left behind. The silent shapes in the dark hold the final verdict on what lit the universe, waiting for our radio telescopes to trace their ghostly contours. Mapping those ghostly bubbles requires listening to a whisper from the deepest dark, a time before the first stars even flickered. This is the ultimate observational frontier, the cosmic dark ages and the very opening moments of reionization. While the later stages of reionization are challenging to study, this earlier epoch is in a class of its own. It is a period of profound silence where the universe held its breath between the fading glow of the Big Bang and the first spark of a star. Here, the usual tools of astronomy fail us completely. There are no brilliant quasars to act as cosmic flashlights, no galaxies to serve as signposts. The only source of information is the faint, pervasive radio hum of neutral hydrogen itself. The 21-centimeter line stretched to even longer, lower frequencies by the expansion of the universe. To observe the dawn of the first structures, we must tune our instruments to frequencies below 200 MHz, a part of the radio spectrum that is a battleground of interference. At these wavelengths, the signal from the infant cosmos is not just faint, it is drowned out by a roaring cacophony. The radio glow from our own Milky Way galaxy is millions of times brighter. The ionosphere, a layer of Earth's upper atmosphere, bends and scatters these low-frequency waves like a funhouse mirror. And then there is the ever-present noise of human civilization, from FM radio broadcasts to satellite communications and even distant radar pulses, all creating a deafening static that can mask the cosmic signal entirely. To have any hope of hearing the universe's first murmur, astronomers must become cosmic hermits. They build their telescopes in some of the most remote, radio-quiet locations on the planet. Places like the Murchison Radio Astronomy Observatory in the vast, empty outback of Western Australia or the Karoo Desert in South Africa. These sites are chosen for their natural radio silence, shielded by geography and sparse population. But location is only the first step. The telescopes themselves look nothing like the gleaming dishes we imagine. Projects like the Murchison Widefield Array and the Hydrogen Epoch of Reionization Array, or HERA, resemble sprawling fields of simple, stationary metal spiderwebs or wooden crosses. These are phased arrays, thousands of simple dipole antennas working in concert to digitally scan the sky. They do not move, they listen. Their goal is not to take a pretty picture, but to collect an ocean of raw data, petabytes of radio noise over years of observation. The real magic and the immense challenge happens in the supercomputers. Sophisticated algorithms are tasked with an almost impossible chore, modeling and subtracting every known source of interference with exquisite precision. They must create a perfect digital model of the Milky Way's radio glow and subtract it. They must account for the distorting effect of the ionosphere moment by moment. They must identify and remove the fingerprints of every passing satellite and far-off radio station. It is a statistical excavation, sifting an entire beach of noise to find a few grains of cosmic sand. The signal they seek is not a clear tone, but a specific, subtle pattern in the radio background temperature across the sky. A detection would appear as a faint, patchy modulation, a shadow of the very first density fluctuations that would one day become galaxies. The pursuit is a heroic effort in patience and precision, where a single misplaced assumption or an unmodeled source of radio frequency interference can set back years of work. It is a testament to our desire to witness the universe's very first chapter, to hear the silence before the symphony began. Success would open a window into a time we have only ever theorized about, revealing the seeds of all cosmic structure. Failure or a continued great silence would be a message just as profound, telling us that our understanding of these primordial conditions is fundamentally and beautifully wrong. But even the most heroic efforts to hear the universe's first murmur must confront its most dominant, silent component. For all our talk of stars and galaxies, of ultraviolet photons and ionized bubbles, we have been discussing the luminous 5% of the cosmos. The remaining 95% is dark, a realm of dark matter and dark energy that we cannot see, only infer from its gravitational influence. This raises a profound, almost heretical question. Could the dark universe itself have played an active role in lighting up the dawn? Could the properties of dark matter have directly steered the course of reionization? This is not a fringe idea, but a serious frontier in cosmology. The standard model assumes dark matter is cold, meaning its particles move sluggishly. This cold dark matter beautifully predicts the large-scale cosmic web we observe, but it also predicts a universe teeming with countless tiny dark matter halos, the very ones that seem to be missing as satellite galaxies around the Milky Way. What if dark matter is not cold but warm? In this model, dark matter particles would have a small amount of inherent motion, a slight warmth that prevents them from clumping on the smallest scales. This warmth would act like a cosmic sieve, smoothing out the tiniest density fluctuations. The result would be a dramatic suppression in the number of the very smallest halos that could form in the early universe. Remember, these tiny halos are the potential hosts for the faintest, earliest galaxies. If warm dark matter is real, then that vast hidden population of ultra-faint dwarf galaxies we have been searching for to balance the photon budget might never have existed at all. The cosmic landscape would have been far emptier on small scales from the very beginning. This would force a complete recalculation of the reionization story. Without a legion of faint sources, the ionizing light would have had to come from fewer, brighter, and more efficient galaxies, putting immense pressure on their escape fractions and star formation rates. The topology of the ionized bubbles would shift from a fine, webbed foam to a pattern of larger, more isolated spheres. The entire character of the era would be dictated not by the luminous actors, but by the hidden nature of the dark stage upon which they performed. But the influence of dark matter could be even more direct and startling. What if dark matter was not completely dark? Most models assume dark matter particles only interact through gravity. But what if they can also interact with themselves or with normal matter in other, very subtle ways? Some theories propose that dark matter particles could annihilate when they collide, converting their mass directly into energy, including gamma rays and other particles that could cascade into ionizing radiation. Others suggest certain dark matter particles could be unstable, slowly decaying over billions of years and releasing energetic photons in the process. In the dense, crowded centers of the first dark matter halos, these processes could have generated a persistent, diffuse glow of ionizing radiation. This would be a light source utterly disconnected from stars or black holes, a ghostly illumination emanating from the dark sector itself. This background glow could have provided a crucial pre-ionizing or supplemental ionizing field, gently warming the gas and making it easier for the first stellar ultraviolet radiation to finish the job. It would be a cosmic collaboration between the seen and the unseen, where the dominant matter in the universe secretly helped illuminate its own structure. The implications are staggering. If such signals were detected, perhaps as an unexplained excess of certain radiation from the early universe or a specific pattern in the 21-centimeter signal, it would be our first tangible clue to the true identity of dark matter. We would learn that the cosmic dawn was not just lit by the fires of fusion, but also by the hidden fires of the dark universe, a partnership that shaped everything we see in the light. The dark universe may have set the stage, but the luminous actors performed within an invisible framework of their own making. As the first stars blazed to life and died in cataclysm, they did more than forge atoms and flood space with light. They may have also woven the universe's first great magnetic tapestry. Today, magnetic fields are everywhere, threading through galaxies, guiding cosmic rays, and shaping the birth of stars. But in the pristine darkness before the cosmic dawn, the cosmos was likely devoid of any large-scale magnetism. The question is, when and how did this fundamental force emerge to sculpt the evolving universe? The seeds of these fields were probably unimaginably small. Quantum fluctuations stretched to cosmic scales during inflation, or perhaps generated in the violent plasmas of the first moments after the Big Bang. For hundreds of millions of years, these seeds lay dormant, weak, and disorganized. Then came the first generation of stars. Their furious stellar winds, rushing out at millions of miles per hour, could have acted like cosmic bellows, stirring and stretching these weak magnetic field lines. But the real amplifier likely came with the star's death. A supernova explosion is not just an expanding ball of fire, it is a maelstrom of turbulent, magnetized plasma. As these colossal shockwaves ripped through the surrounding gas, they could have dramatically amplified those primordial magnetic seeds, injecting organized magnetism into the intergalactic medium for the first time. This process, known as a dynamo, is like a child on a swing, giving small, timed pushes that build into a huge arc. The supernova's turbulence provides the push, turning chaotic motion into ordered magnetic energy. Once established, even a faint magnetic field could have played a subtle but crucial role in the reionization saga. How magnetic fields exert pressure. In the tenuous gas between galaxies, this pressure is minuscule compared to thermal or gravitational forces. But in the dense, delicate environments where the first galaxies were struggling to form, it could have been a deciding factor. Imagine a cloud of gas on the verge of collapse. Without magnetism, it fragments under gravity alone. But with even a weak magnetic field threading through it, the field lines resist being squeezed. They provide a kind of skeletal support, potentially slowing the collapse and altering how the cloud fragments into stars. This could have changed the initial mass function of the first stars, perhaps producing fewer of the monstrously large population 3 stars and more of a moderate size. A shift in the very first stellar population would have ripple effects through everything that followed, from the rate of metal production to the intensity of the ultraviolet background. Furthermore, these nascent magnetic fields could have influenced the expansion of the very ionized bubbles we have been discussing. As an ionization front, a wall of ultraviolet radiation plows into neutral gas, it drives shocks ahead of it. Magnetic fields within that gas would channel and shape those shocks, potentially making the bubbles expand more easily along field lines and resist expansion across them. Instead of perfect spheres, the bubbles might have become slightly elongated, their shapes whispering the orientation of the invisible magnetic fields that guided them. While magnetism was almost certainly a secondary player compared to the raw power of radiation and gravity, its potential influence makes it a fascinating subplot. We cannot yet observe these primordial fields directly. Their signature would be imprinted in the polarization of light from the earliest sources, or in the subtle way they affect the 21-centimeter signal from neutral hydrogen. Detecting them would open a new window into the astrophysics of the infant cosmos, revealing not just where the light came from, but the hidden structure of the stage upon which the entire drama of reionization unfolded. These textbook-shaking discoveries come from a single, golden mirror in the cold dark of space. The James Webb Space Telescope was built to see the cosmic dawn, but what it is showing us is forcing a complete re-evaluation of what that dawn actually looked like. Webb is finding galaxies that are not just ancient, they are shockingly mature. At redshifts above 10, meaning we see them as they were when the universe was less than 500 million years old, Webb has spotted galaxies that are massive, bright, and already filled with complex dust and heavy elements. According to our most trusted models of cosmic structure formation, these galaxies should not exist. They simply did not have enough time to gather so much mass, form so many stars, and forge such an abundance of metals. It is like finding a fully grown oak tree in a forest you planted only a year ago. The universe, it seems, was building complex structures far faster and more efficiently than we ever dreamed. This presents a direct and thrilling challenge to the story of reionization. If galaxies this bright and evolved were common in the very early universe, then the cosmic landscape was not a sparse scattering of faint, struggling embers. It was already dotted with brilliant beacons. The immediate question for reionization is one of raw power. Could these unexpectedly bright galaxies have been the primary engines of ionization all along? Their stellar populations, likely already enriched with metals from earlier generations of stars, might have been producing ultraviolet radiation at a ferocious rate. More importantly, their very maturity suggests they could have been structurally different from the simple, turbulent blobs we often picture. They might have had stronger stellar winds or more organized outflows, carving clear channels through their gas and allowing a higher percentage of their ionizing photons to escape. A universe filled with these efficient, bright factories could have completed reionization much earlier and more decisively than our old models allowed. But this solution creates new puzzles of its own. How did these galaxies get so big so fast? It forces us to reconsider the very first steps of structure formation. Perhaps the initial seeds of dark matter halos were far more massive than we thought, giving them a gravitational head start. Or maybe the first stars formed with unbelievable efficiency, converting nearly all available gas into stellar mass in a single explosive burst. There is even the radical possibility that our understanding of the early universe's expansion or the nature of dark matter needs revision to allow for such rapid growth. Every new deep field image from Webb is a potential revolution, each bright smudge of light a challenge to our timelines. For the story of reionization, these galaxies are not just new characters, they are protagonists demanding a rewrite of the entire script. They suggest the cosmic dawn was not a slow, hesitant brightening, but a sudden, brilliant flash, orchestrated by a generation of galaxies that achieved in a few 100 million years what we thought should take a billion. The textbooks are not just being updated, they are being torn apart and reassembled, one stunning infrared image at a time. The most startling clue from the cosmic dawn might not be a detailed map, but a single, baffling number. While the dream of 21-centimeter tomography is to create a three-dimensional movie of the reionization era, a simpler, more profound measurement has already sent shockwaves through cosmology. This is the global 21-centimeter signal, and it asks a different question. Instead of showing where the bubbles were, it tells us how cold the average hydrogen gas across the entire universe was at different moments in time. Think of it as the universe's average body temperature chart from infancy through adolescence. To measure it, you don't need a complex radio array to make an image. You need an exquisitely sensitive radio antenna that listens to the whole sky at once, capturing the average radio brightness at specific frequencies. Each frequency corresponds to a different cosmic age. The expected story was straightforward. Early on, the hydrogen gas should have been slightly warmer than the cosmic microwave background. As the first stars ignited, their ultraviolet light would have gently warmed the gas, bringing its temperature closer to that of the background glow. But then, something remarkable should have happened. The fierce radiation from these first stars and the subsequent X-rays from early black holes would have heated the gas dramatically, making it much hotter than the CMB. So the predicted global signal was a gentle curve, a shallow dip into absorption when the gas was colder, followed by a rise into emission as it heated up. Then came the EDGES experiment, a small, unassuming radio antenna in the remote Western Australian outback. In 2018, its team reported a result that defied all expectations. They claimed to have detected the absorption part of the signal, but it was far deeper and sharper than any standard model could explain. The dip was about twice as deep as predicted, suggesting the primordial hydrogen gas was profoundly cold, much colder than anyone thought possible, at a time when the first stars should have been warming it up. This was like taking the universe's temperature and finding it in a state of deep cosmic hypothermia. The implications were immediate and revolutionary. For the gas to be that cold, it must have been losing energy to something else at an incredible rate. One leading explanation points a finger at the dark universe. What if the cold hydrogen atoms were interacting with even colder dark matter? In some theoretical models, dark matter particles could have collided with hydrogen, acting like a cosmic heat sink and siphoning away thermal energy, chilling the gas to these unexpected depths. Another possibility is even stranger. Perhaps the early universe was flooded with an intense background of radio waves, perhaps from the frenetic activity of the first stars and black holes, which made the cosmic microwave background itself appear brighter in comparison. This would make the hydrogen seem colder by contrast, creating a deeper absorption signal without the gas itself being so frigid. Both explanations require physics beyond our standard models. The EDGES result remains hotly contested. The difficulty of this measurement cannot be overstated. Isolating this faint, all-sky signal from the roaring foreground of our own galaxy's radio emission is a monumental task akin to listening for a single, specific note in a symphony played by a million orchestras simultaneously. Many scientists question whether the EDGES team successfully removed all that galactic noise, or if the startling signal is merely a ghost in the data, an artifact of imperfect calibration. This controversy has ignited a global race for confirmation. New experiments with different designs, like the radio experiment for the analysis of cosmic hydrogen in India and the large aperture experiment to detect the dark age in South Africa, are now listening to the same ancient frequencies, each using unique methods to control for errors and cross-check the result. They are not just trying to see if the signal is real, they are trying to trace its precise shape across time. A confirmed detection of such an anomalous dip would be one of the most significant discoveries of the century, offering our first direct experimental hint of an interaction between normal matter and dark matter, or revealing a previously unknown source of energy in the infant cosmos. It would mean our story of the cosmic dawn is missing a fundamental chapter, one written not in light, but in the profound and unexpected chill of the primordial dark. The brilliant galaxies that lit the cosmic dawn did not simply vanish when their work was done. Their ultimate fate is the final, haunting mystery of this era. What became of those pioneering stellar cities after they flooded the universe with light? Their stories diverge, a cosmic tale of mergers, transformations, and quiet deaths. For many, especially the smaller building blocks, their destiny was to be consumed. The early universe was a violent construction site governed by gravity's relentless pull. Small proto-galaxies, drawn together by the dark matter scaffolding of the cosmic web, would have collided and merged over and over again. Through a hierarchy of cosmic cannibalism, these early sparks were assembled into the majestic spiral and elliptical galaxies we recognize today, like our own Milky Way. The brilliant beacons that drove reionization became quite literally the bricks and mortar of the modern cosmic city, but not all journeys ended in a merger. Some of these first galaxies may have met a far lonelier end. The very processes that made them effective, their fierce radiation and powerful supernova, could have sealed their fate. This is feedback in its most brutal form. In smaller galaxies with weaker gravity, the explosive energy from multiple stellar explosions might have simply blown all the remaining gas, the fuel for future stars, completely out of the galaxy. With its gas reservoir ejected into the void, the galaxy would be quenched. Star formation would cease abruptly, leaving behind a dormant, fading relic, a galaxy frozen in time from the epoch of reionization. We might be able to spot such fossils in our local universe, small, faint galaxies made almost entirely of ancient stars with no young blue stars to be found. They would be the ghost towns of the cosmic frontier, silent monuments to an age of fire. So how do we trace these lost ancestors? We become cosmic archaeologists, but instead of digging in the earth, we read the light of ancient stars. The key is in their chemical signatures. Remember the first supernova from population 3 stars? They polluted the early gas with specific primitive patterns of elements. Stars that formed from that first wave of pollution, the true second generation, carry a unique chemical fingerprint, very low in overall metals, but with a specific ratio of elements like carbon, oxygen, and iron that acts like a birth certificate from the reionization era. Astronomers hunt for these fossil stars within the halo of our own Milky Way. Our galaxy's halo is a vast spherical cloud of old stars and globular clusters that surrounds the galactic disk. It is an archaeological dig site containing stars captured from smaller galaxies that merged with the Milky Way long ago. By analyzing the spectrum of these ancient halo stars, we can find ones with that pristine, early chemical signature. They are living artifacts, stars that were born in those first small galaxies that drove reionization and later swallowed by our growing galactic home. This stellar archaeology extends beyond the Milky Way. In nearby dwarf galaxies like Sculptor or Fornax, we find ancient stellar populations with similarly primitive chemistries. These small galaxies might themselves be the surviving, quenched descendants of the reionization era, systems that managed to avoid major mergers but had their star formation snuffed out early. By studying them, we get a direct look at the building blocks of larger galaxies, frozen in a simpler state. Every ancient star we catalog is a piece of the puzzle. Their motions tell us about the gravitational pull of the dark matter halos they formed in. Their chemistry tells us about the specific supernova that enriched their birth clouds. Together, they allow us to perform a kind of galactic genealogy, reconstructing the family tree that leads from the first flickers in the dark to the grand spirals shining in the night sky today. The story of reionization does not end with a transparent universe. It ends with us looking up and searching for the oldest stars, whose ancient light carries the memory of the universe's fiery awakening, a story written in atoms forged in the very first dawn. From the silent collapse of the first dark matter halos to the fading glow of ancient stellar fossils, every mystery we have explored is a single thread in the same grand tapestry. The identity of the first light sources, the patchiness of the ionized bubbles, the impossible growth of early black holes, and the chilling whisper of the global 21-centimeter signal, these are not isolated puzzles. They are interconnected symptoms of the universe's single greatest transition. The escape fraction of photons dictates the timeline constrains the sources. The nature of those sources determines the topology of the bubbles, and that topology imprints itself on the ancient light we are straining to detect today. To tug on one thread is to feel the tension in all the others. This is the beautiful, maddening complexity of the Cosmic Reionization Era. We are no longer staring at a blank page in the cosmic history book. We are holding a manuscript where most of the words are still faded, the paragraphs out of order, and the most crucial passages written in ink we cannot yet see. But the tools to translate this ancient text are now coming online. The James Webb Space Telescope is revealing the galaxies we thought couldn't exist. The Future Square Kilometer Array is tuning its ears to hear the hydrogen song from the dawn of time. Next-generation cosmic microwave background experiments are preparing to measure the polarization of the afterglow with microscopic precision. Each is a different kind of decoder ring for the same epoch. What we are witnessing is not just incremental science. It is the opening of a window that has been sealed for 13 billion years. We are living in the unique moment when the universe's own childhood diary is being cracked open, its first chaotic, formative memories finally coming into focus. The answers will rewrite our understanding of where we came from, what galaxies are, and how light conquered the dark. This story belongs to anyone who has ever looked up at the night sky and wondered. So stay curious. The next chapter is being written right now, and you are here to read it. For more journeys to the edge of our understanding, make sure you are subscribed. The cosmos has only just begun to share its secrets.